All right, let's dive right into an explainer on a classic physics puzzle, Irodov's problem 1.198. It's a fantastic problem because it really forces us to see how three big ideas, linear momentum, kinetic energy, and angular momentum, all have to play together to give us the final picture.
So, here's the setup. You've got a dumbbell just sitting there minding its own business, and then bam, a little ball comes in and smacks one of the ends head on. The big question is, what happens next? Does the whole thing just slide forward? Or does that off-center hit make it start to tumble and spin through space? That's exactly what we're going to figure out.
And here's our game plan. First, we'll set the scene for the collision. Then we'll go over the physics laws we need, our rules of the game. We'll analyze what happens right after impact, find the motion of the dumbbell center, and then we'll get to the main event, calculating its spin. We'll wrap it all up with the big takeaways.
Okay, let's get started. Like with any physics problem, the very first thing we have to do is get organized. We need to define all the players on the field, what they are, how much they weigh, and what they're doing before the action starts.
So here's the whole situation laid out nice and clear. We've got the ball with mass m, and it's coming in with some initial velocity we'll call v0. The dumbbell is just sitting there, so its velocity is 0. Each of its spheres has a mass of m over 2. Now, after the collision, the ball is going to have a new velocity, v1, and the sphere that it hit is going to have a velocity, v2. Our first mission is to find out what those two new velocities are.
Now, to figure this out, we can't just pull numbers out of thin air. We've got to use the fundamental laws of mechanics. These are basically our toolkit for breaking down any kind of collision.
And the most important word on this slide is elastic. Seriously, this one word is a huge clue. It tells us that two different things are conserved, meaning they don't change before and after the collision. We've got conservation of momentum, and we've got conservation of kinetic energy. It's basically a perfect collision, where no energy gets wasted as, heat or sound.
And this is the thing we're actually trying to find, the proper angular momentum. I know, it sounds a little fancy, but here's all it means. Imagine you could shrink down and ride on the exact center of the dumbbell as it's flying and spinning. From your point of view, it wouldn't be moving forward at all. You'd just see it spinning around you. That spin, completely separate from the forward motion, that's the proper angular momentum. All right, we've got our rules. Now let's apply them to that split second right after the impact and see how fast everything's moving.
So, we write down our two big equations. First, conservation of momentum. All the momentum the ball had before has to be shared between the ball and the hit sphere after. Second, conservation of kinetic energy. Same idea, but with the energy of motion. Now here's the great part. We have two equations and two unknowns, v1 and v2, which means we can solve it. And when you do all the algebra, you find that the ball bounces back with 1/3 of its original speed, and the hit sphere shoots forward with 4/3 of the ball's original speed.
Okay, cool. So we know how fast the individual pieces are moving. But what about the dumbbell as a whole object? How is it moving?
To separate that forward motion from the spin, we need to find a special point, the center of inertia, or you can call it the center of mass. The velocity of this one point tells us how the entire dumbbell system is moving forward through space. It's really just the average velocity of its parts, but weighted by how much mass each part has. And here's how we calculate it. We just use the standard formula. We add up the momentum of each part, the hit sphere and the untouched sphere, and divide by the dumbbell's total mass. Since the second sphere hasn't moved yet at the instant of collision, its momentum is just 0. The math works out really nicely, showing that the center's velocity is just half the velocity of the hit sphere. And since we already know v2, we can plug that in and find the center of the dumbbell moves forward at 2/3 of the ball's original velocity.
Okay, this is it. This is the payoff. We have all the pieces of the puzzle. To isolate that pure spin, we're going to do a little mental jump. We're going to imagine we are in a reference frame that's moving right along with the dumbbell's center.
So from this new point of view, the dumbbell itself isn't actually going anywhere. It's just rotating. The two spheres look like they're moving in opposite directions around the center point. And to find these new relative velocities, all we have to do is take their actual velocities and subtract out the velocity of the whole system, vc. And now, finally, we can calculate the angular momentum in this special C frame. For each sphere, we just take its distance from the center, which is L over 2, and multiply it by its momentum in this moving frame. And here's the really cool part. Both spheres end up giving the exact same amount of angular momentum. One's moving forward and one's moving backward relative to the center, but both of those motions create a spin in the exact same direction, so they just add up perfectly.
So, we've done it. We've found the answer. But just getting the right number is only half the job. Let's take a step back and think about the really important lessons this problem teaches us.
And here it is, the final result. The proper angular momentum is 1/3 times L times m times v naught. Isn't that neat? You can see exactly how the spin depends on the dumbbell's length and the initial wallop from the ball. We've just taken this chaotic-looking collision and boiled it down to this one clean, elegant expression using nothing but first principles.
Now, to really lock this in, it's super important to know the traps you can fall into. The number one mistake is mixing up your reference frames. You can't use a velocity from the ground's perspective in a calculation that's happening in the dumbbell's moving frame. Another big one is just forgetting that elastic means you have to use both momentum and energy conservation. And of course, remember that proper angular momentum isn't just about any old point. It has to be calculated around the center of inertia.
So I'll leave you with a question to think about. Looking at that final equation we found, what do you think would happen to the dumbbell spin if the ball that hit it was twice as heavy? Would the spin just double, or is it more complicated than that? You now have all the physics you need to figure it out. Thanks for working through this one with me.